morning, grade 11s. Today is Monday, June 15th of 2020, Coronachem day 42nd. This is my second attempt to teach this class. I spent half an hour teaching on Friday, and when I went to upload it, I did a wrong move on the phone and I lost the whole half hour of teaching, and I was so annoyed that I just said, okay, we'll do it on Monday. And I guess you enjoyed your little break on Friday. So today we're going to continue with a chapter 10 review. Then we'll do a little bit of review of the organic chemistry chapter, and then I'll combine the test for those two chapters, and that'll be it. This is the last week, folks, so let's do one last push, and then you'll be ready to go to university. So there are 10 concepts that I'd like to review with you. Actually, let me put it so that, okay, that's better, I think. I like to stand to the left side of the board. So there are 10 concepts I'd like to review with you from chapter 10. The first is that, so gases is the chapter, and it's from chapter 10 of the book. The first concept is that pressure is equal to force over area. Now, force is in newtons, area is in meters squared. When you combine those two units, you get a unit called the Pascal. And you just symbolize it with P. A force of 1 Newton is the weight, basically, of an apple in Earth gravity. So imagine the weight of an apple distributed over an area of 1 meter squared. You would get a pressure of 1 Pascal. So 1 Pascal, Pascal is not a very big unit. It's a small unit of pressure. In fact, atmospheric pressure requires 101,325 pascals, and that equals about 14.7 pounds per square inch, which brings me to the next idea, which is what are the different definitions of atmosphere. So 1 atmosphere is the pressure exerted by all the gas in our atmosphere, which obviously has a weight exerted caused by gravity. Now, air molecules move around at roughly 400 meters per second at room temperature, and they bounce off each other with perfectly elastic collisions, but you can actually force them together because there's a lot of empty space between them. So if you can imagine a room full of ping pong balls all bouncing around continuously without ever stopping, that's somewhat reminiscent of what air molecules are like. And because they're compressible, as you go deeper and deeper into the atmosphere, the molecules are closer and closer together because there's the weight of all the other molecules pressing on top of them. If you were to take a 1 inch square, 1 inch square is about that big, of the air, and put it into a container that went all the way to the top of the atmosphere, that stack of air would weigh 14.7 pounds. And that's the basis of atmospheric pressure, that 14.7 pounds of pressure exerted on every square inch of every surface on the Earth is what constitutes atmospheric pressure. Why don't we feel it? Because we have the same pressure inside of us. But you can feel it if you suddenly decompress. Say if you climb very quickly up a hill up a steep hill on a fast-moving car, you'll feel your ears pop, and that's because you're changing the pressure of the air that is pressing on your eardrums, which are very sensitive to air pressure, is changing. Your eardrums are so sensitive to air pressure that they have a special tube connecting your eardrum, the empty space inside your head, meaning the one behind your eardrum, that connects to your throat, that helps to equalize the pressure. All right, so when you equalize that, if you don't equalize that pressure, any change in pressure of the atmosphere would be immediately painful, because you wouldn't be able to equalize it, and your eardrums are exquisitely sensitive to air pressure changes because the job they have to do is to sense vibrations of air. That's how we hear each other. So there are various things you should memorize where you interconvert pressure. You should say 1 atmosphere equals 760 torr, which equals 760 millimeters Hg. which equals 101,325 pascals, which equals 101.325 kilopascals, which equals 14.7 pounds per square inch, to go back to the old English measures. If you ever read an old barometer, that equals 22 inches of mercury. So 29.2 inches equals 760 millimeters. In the old barometers, this would be normal atmospheric pressure. You see sometimes barometers have a dial that pushes at different pressures. If you have a low pressure zone, it usually means there's a lot of moisture in the air. When you have a lot of water vapor in the air, it actually lowers the average density of the air in that area, and it will lower the air pressure. So whenever you have a low pressure zone moving in, that's normally associated with high water content in the air, which usually means clouds, rain, and moist air. And if you go to the other end of the scale, when the air is very dry, it tends to have a higher density, higher oxygen content, and so on, and tends to be also associated with sunny weather. Am I reading anything out? Yeah, you could also talk about 1.01325 bar. That's the new one of the new measurements. I remember when I was a kid, they used to quote air pressure in millibar on the Weather Channel. So all these are the same pressure. They're interchangeable. Which ones do you normally see being used? This one gets used a lot, and this one gets used a lot. Brings us to the ideal gas law. The ideal gas law is basically a combination of the research of the three different laws: Boyle's law, Charles' law, and Avogadro's law. All of them basically combine into the ideal combined gas law. P1V1 over N1T1 is equal to P2V2 over N2T2, where pressure, P is pressure, V is volume, N is number of moles, T is temperature. So you can have an initial set of conditions and a final set of conditions. So if you have two set of conditions, you can tell what the air is going to do. So air can be compressed, and if you have a volume of air which is constant, if you have an amount of air which is constant and a constant temperature, you could actually eliminate that part of the equation, and you get Boyle's law. If you have a constant pressure and volume, you'll get 1 over N1T1 or 1 over N2T2. Just eliminate any part of the equation that remains constant before and after, and it helps to simplify the mathematical calculation. If you have one set of conditions, by the way, you can just enter them, and pressure and volume is proportional to, or is actually equal to, the number of moles of gas times the gas constant times the temperature in Kelvin. Temperature always has to be the absolute temperature, meaning you have to use a temperature scale which recognizes that there is a temperature at which you cannot go lower. What's the coldest temperature you can reach in the universe? It's minus 273.15 Kelvin, Celsius. You can't go colder than that because there's no more heat. Once there's no more heat, you can't get any colder. So the coldest temperature you can reach in the universe is what they call absolute zero. At that point, you have a solid where the atoms aren't even jiggling anymore because there's no more kinetic energy in them. So you have a perfectly cold substance, just like you can have a perfectly darkened room. Once you get dark, you can't get darker than dark. Once there's no more light, you can't get darker. You can't go to Walmart and buy a dark bulb and make the room darker by switching it on. There's no such thing really as dark. This is absence of light. But what we call darkness is sometimes not really darkness because there's still little vestiges of light. Maybe an animal with bigger eyes or a more sensitive apparatus will be able to detect something in the dark if their eyes are better adapted than ours for going around in the dark. So the true darkness means total absence of light. Just like absolute zero means the total absence of heat. So sometimes people have a hard time understanding that there's still heat energy in very cold objects as long as they're above absolute zero. You could take liquid nitrogen. Liquid nitrogen, if you stick your hand in it for a minute, your hand will freeze solid. You'll be able to break it off on the table. But liquid nitrogen still has some heat energy in it because it's only at minus 196. It could still go another 80 degrees colder, and then you would get solid nitrogen. If you took out all the kinetic energy from the molecules of nitrogen, you would then get solid nitrogen. And this is an observation, by the way, that a guy by the name of, well, they end up calling him Lord Kelvin. I don't know if that was his original name, forget his original name, but he was named a knight for discovering, I don't know if it was because of that discovery, we maybe made other discoveries, but he did discover that when you cooled gases down and you plotted their volume versus temperature, he noticed that all the lines for all the different gases converged on a point where there was zero volume and the temperature was minus 273. So he realized at that temperature something special was going on, meaning that there was no more energy in the gas. And that's how we discovered the absolute temperature. So the absolute temperature is what you need to use when you do any of these calculations, and in fact any thermodynamic calculations, it's important to use the Kelvin scale. So PD equals nRT. This value R is a constant that is used to make all the units work together to give you a proportionality. So the ones that we like to use, the most popular one, and this is the fourth idea. Fourth idea is that R equals 0.082057 if you have units of liter atmospheres per Kelvin mole. We like to use atmospheres because it's easy to memorize the pressure of one atmosphere. It's one. Our atmosphere exerts a pressure of 1 atmosphere. Pretty easy to memorize. If you go on Venus, the surface pressure on Venus will amaze you. It's about 100 atmospheres. The Venusian atmosphere is 100 times thicker than the Earth's atmosphere, also because of the very high carbon dioxide content, which traps heat energy. The temperature of Venus is something like 800 Fahrenheit. So it's hotter than your conventional oven. You can turn your oven all the way up to the maximum. It's still not as hot as the surface of Venus. So not a very hospitable planet. It would have to lose great parts of its atmosphere to become hospitable. It's only 2/3 of the distance to the sun as the Earth is. So it's 67 million miles from the sun, whereas the Earth is 93 million miles. It shouldn't make that much of a difference, but evidently it does, because it's a completely inhospitable planet. Another version of R that we use, and which is quite popular because it's thermodynamically useful when you want to convert to joules and so on, is with units of liters per kilopascal per Kelvin mole. And incidentally, if you make this 1,000 times bigger and this 1,000 times smaller, you can still use the same number. So you can use meters cubed per Pascal over Kelvin mole, and you'll still get 8.314 as the number. Just be aware of that. One other thing that we should remember with ideal gases, and we developed this whole chapter from the premise that gases behave ideally, because it helps to just simplify the way things are. And back in the 19th century, when scientists were trying to understand what gases were doing, that's what they did. They made some simplifying assumptions, which is what all scientists do when they're at the early stages of trying to understand something. So the simplifying assumption they made with gases was that they were composed of tiny little molecules, which were almost geometric points, meaning they have no zero volume, which is pretty close to true, because molecules are incredibly, vanishingly small. And the other idea that they assumed was that when molecules bump into each other, they don't really interact. They act like billiard balls. The billiard balls don't stick to each other in any way. But as it turns out, gas molecules do interact a little bit. Imagine two long chain alkane molecules like decane colliding each other in the vapor phase. They're like two long spaghetti noodles. If two long spaghetti noodles were to collide in space, they would sort of wrap around each other, and then maybe they would flip off, but they would continue going their way, but they would momentarily interact. So those assumptions that scientists made are not 100% accurate, but it allowed them to do calculations that would otherwise have been too complicated with all the other variables. And so they came up with this ideal gas law, PV equals nRT, and it's pretty good at predicting what gases will do, especially if the temperature is high and if the pressure of the gas is low. Why would that be the case? Well, when the temperature is high, the molecules are moving really quickly. So the time they spend in proximity of each other is going to be pretty short. And the other assumption says that they have very little attraction to each other. Well, at low pressures, there's fewer interactions between molecules. So even if they do have a little bit of attraction for each other, it'll be less of an issue because there's fewer interactions between the molecules. When you start pressurizing the gas and forcing the molecules to be closer together, then you're going to get more frequent interactions, and if they're attracted to each other, it's going to have an effect. So that's where van der Waals equation comes in, but that comes in towards the end. I want to talk about that's the 10th point. The 5th point I want to talk about is the volume of an ideal gas. And Amedeo Avogadro, where did I put my marker? Oh, put it in the wrong pocket. Amedeo Avogadro said that the molar volume of any gas is the same as long as the pressure and the temperature are the same. And within a reasonable approximation, this is true. All gases have a volume of around 22.41 liters at STP is what they call it, standard temperature and pressure. What is the standard temperature? 0 degrees Celsius or 273.15 Kelvin, and the standard pressure is 1 atmosphere. So if you take 1 mole of gas at STP, it'll have a volume of 22.41 liters. This is what, I don't know if Amedeo Avogadro actually said exactly those words, but that's what it boils down to. Also, when you're talking about density of gases, because the density of gases does come up in calculation, again, it's always the same thing. Density is equal to mass over volume, but the units that I like to use for gases are grams per liter, not per milliliter, because gases are about 1,000 times less dense than something like water, say. The atmospheric gases are a density around 1.2 near room temperature, whereas water has a density of around 1.2 grams per liter, whereas the density of water is 1 gram per milliliter, which is 1,000 times smaller. So don't fall into that trap. In fact, the book has a mistake in one of the problems where they quote the density of a liquid. So I forget which chapter it is in, but they say grams per milliliter. So it gives you an answer that's 1,000 times higher than it's supposed to be. So just pay attention to that. It's a typical pitfall. Number 7 idea is that all the gases contribute equally to the pressure in proportion to their mole fraction. So a way of saying that is the total pressure exerted by any mixture of gases is equal to the pressure exerted by gas 1 plus the pressure exerted by gas 2 plus the pressure exerted by gas 3, etc. And it's directly proportional to the mole fraction. So if each one of the gases is 1/3 of the mole fraction, then each gas will contribute 1/3 of the pressure. If it was, say, a 60-30-10 mix, then this one will exert 60% of the pressure, that one exerts 30% of pressure, and so on. So that's the law of partial pressures, and there was a question I used to ask all the time, and will in future also continue to ask, was how did the NASA scientists resolve the issue of fire hazard from breathing pure oxygen, which ended up killing 3 astronauts. In Apollo 1, all 3 astronauts died, and I think the circumstances of their death